like both photons and photons out of a gallium arsenide. Look at them in coincidence and detected them that way. And when it's liquid helium, in a superfluid state, and the liquid helium can produce photons and protons. Those the particle scatters and come around when they reach this interface between liquid helium and vacuum and cause individual atoms to be evaporated from the air. And those can then adsorb one or little silicon particles and be made that way. Helium is a very bright scintillator, like the other double liquids. They can detect the photons. Okay, now in terms of the experimental philosophy, what we've done is an approach where we have a set of shielding that can be easily taken apart, taken out on rails, so that we can access the experiment very easily to switch out. The whole thing is built from the refrigerator. Center of the experiment is built with low radioactivity materials. There's an experimental volume here in red that's hanging from the vibration isolator in order to keep any vibrations down to from 10 minus 9 square meters overall. We put a log together to keep it electromagnetic vibration backgrounds. We're going to have two identical setups, just like this, each installed in deep underground laboratory. In practice, we're going to have two of these setups, one in their individual clean rooms deep underground. And that way we can, if we have one detector type, which really very nicely, we do what's called the experiment. We can switch out different detectors in the other class and keep doing iteration of those at the same time. This gives us a lot of operation. Now, my admit in this field has been the discovery over the past few years that there was a substantial amount of condensed matter background in these detectors. And there's still a lot of R&D going on to understand this background. But if you go down one of these experiments and you look at the rate of events that you see it decreasing in time over a number of different experiments in this field, CREST and TESSERACT and others. And this is time dependent and dropping considerably as you keep running your experiment. But it's always at really a pretty high rate compared to what we're used to in xenon experiments, for example. That's not dark matter. You can expect dark matter to be changing in time like this. And it varies from detector to detector. And so, this is a major issue. You can see a lot of effort in the field to understand this, and they're dedicated conferences talking about and it's a lot on sharing how we hold these detectors, how we do the aluminum and tungsten deposition, and protocol is no LED background to some degree. In addition, there's evidence that they have some rate of these LED events that scan the polar gas. So there's something going on in bulk of these materials also using LED events. Now, one thing they do multiple sets of readout channels on individual detectors in order to use this LED ray, and it turned out to help. You separately have two sets of TESs read out independently, collecting the photons out of this silicon. You can plot the event energy in one set of readout from the other set. You see a bunch of events that are associated with one readout, and a bunch of events are associated with the other. And then there's also events that are seen in both. But by picking out the events that are seen in both, which are happening in the bulk, we can reduce this LED background to some degree. But just using that approach, using the dual readout, and a really good imaging equation that we're talking about, we're able to look at new dark matter parameter space. In fact, we have a paper that was just accepted to physical review letters, we were able to look at this little bit of corner of parameter space that had not been probed by other experiments. And this was just by running one of these detectors in basically Berkeley without any shortness. So that can tell you that even with minimal effort, we're already able to do new physics with these sensors. Over here, we're really focused on multiple targets, and I'll describe the ending of each of them. So the sapphire, we've got lunar ions, we've got oxygen, and it turns out that if dark matter can couple through a dark photon, and you use some electromagnetic coupling through the atoms of the sapphire, then if the dark matter is low enough mass, that it can scatter off many of these atoms at once. And having this polar crystal boosts your sensitivity to really low mass dark matter particles. So in this case, we have PDSs and aluminum fins on the sapphire and we get out just like we do with silicon. And we have first sensors that have been fabricated of this type. So sapphire is really focused on really low mass dark matter particles. Another piece of dark matter sensor we do is with gallium arsenide, where our main focus is on the electron frequencies. Dark matter is connected to electrons. It turns out that gallium arsenide has a very low level. Gallium arsenide has a photon level of 125 photons per unit. That's simulated in your infrared. So in that case, what you do is you have a photon detector based on the same technique. You collect the photons, the relation photons from the silicon, and then you also put the photons in the electricity. You look at coincidence between these channels, and you part coincidence for a dark matter emission. That way, you will have these what would be excess factors, which will only occur in one or the other, independent rates in these two different sensors. You're not going to be, I think, really effective for knocking out the backgrounds. Our freight collaborators in Berkeley is mostly focused on silicon and germanium-based detectors, where you collect both charge and photons. If you have a low medium loss with a silicon or germanium, then you can use this ratio of photons to charge and to be able to distinguish between electron recoil background nuclear recoil signal versus these elements. And they say quite a long way through R&D on these targets, especially associated with the ricochet program, which is using these experimental detectors to look for coherent neutrino nucleus scattering at this amount of detectors involved. Using is instead to apply a low voltage on the symmetry for germanium detectors, such that a lot of photons get produced as the electrons get dragged through the detector. This allows you to detect electrons really in time in these 30 to 100 grams to the detector. And by looking for nuclear recoils in between the peaks of these electrons, you're able to get more sensitivity and knock out the LED back. Okay, here's some interesting data from them about when you apply the low voltage, what kind of signals you get in ionization versus phonons. You can see a band for electronic recoils and calibration sources. You can see a band, you can apply neutrons, pass neutrons to the experiment, you get a band for nuclear recoils. And then down at zero ionization yield, you get LED intensity only. So you can then say, oh, I'm going to only look at these red bands to knock out this LED background. Okay, and the final target I'll talk about is superfluid helium. So the nice thing about superfluid helium is that you don't expect any solid state backgrounds. You don't expect this LED to be occurring in superfluid helium. That's basically a way of dealing with these photon bursts is to go liquid where you can't have this stress build up in material. So then if you have an event in liquid helium, ions can cause helium atoms to be evaporated to the liquid helium surface. And then you have an array of those silicon TES-based detectors in the vacuum above superfluid helium. If you have an event in the bulk of helium, you expect photons to be released, or atoms to be released across the surface, to be detected on a variety of different wafers. And again, by looking at residues across different wafers, we can use the background substantially. And the nice thing is we have working detectors that operate on this principle. Here's one that's been run at the University of Massachusetts. And you can see photon signals, we can see scintillation from the helium, from the singular excellence decay. We can see the evaporation pulse, and we can also see signals from triple excellence in superfluid helium. So we basically have working helium detectors that we can take to the ground and look for them. And like we used to look at the ratio of conflict to charge, that's 2 ratio. In helium, we can do something similar. We can look at the ratio of photons to scintillation to get particle beam. And here's just some first data where we can look at for electron recoils in red versus nuclear recoils in blue. You can already see that we have this kind of distribution power. And then we have multiple readout channels. You can see that you can use that technique and calibrate and see events of liquid helium distributed off more than one channel above. Liquid status, we've had a big boom in the past few months. This summer, we had a series of reviews in the United States on TESSERACT. One was a so-called PD138 review, sort of a CD1 equivalent to the DOE system. And then in July, this month, we paid it as a DOE gateway. This is what unlocked equipment money to start buying dilution refrigerators and shielding product equipment, house items for the Tesseract experiment. So this is a major change in Tesseract. We moved from the pre-project phase and design phase into one big project phase, manage the LBL. And so this is very exciting. Development funding through INP3 in France for equipment and postdocs. Basically, one of the dilution refrigerators is being involved in France, with a sense of shielding in France, and a number of permanent staff in postdocs and grad students working on this. And then Switzerland is also supporting Tesseract research here in Zurich, European Institute. So we're really moving into a new stage. We're planning to move underground in 2028. We can allow the process to remote on here in 2028 and start taking the first science data in 2029. In the meantime, we'll be continuing R&D with different targets. We'll be continuing our cryostat and shielding design, commissioning them at LPSC and also in Berkeley, before we bring them underground in 2028. Here's just a current picture of what these setups might look like if we grounded one on. Sort of a lot of effort is about the design and construction of shielding. The idea is that you have these layers of lead, pilot fluid surrounding it, and sort of clamshell design around the cryostat. That's an idea of how that design is coming. Okay, so that brings me to the end. I'll summarize. So we have this state-of-the-art technology. We're able to see events at the sub-EV scale, which is really new for the field. We have the strong Tesseract team across the US and France and Switzerland. We're going to use a variety of target materials and multiple signal channels and a variety of pixel readout in order to reduce background significantly to get past this instrumental background we call polymer. Even small gram scale detectors can have big scientific impact. And it's true in the field. Any of these experiments, if you're looking in open parameter space, could see something. Every time we look in the area of fluid point, you can see dark things. And so it's continuously exciting as we run it. And sensor R&D will continue. We're really focusing now on reading out this variety of targets, and we really can go down in 2028 for our programs. So very efficient. Sure.